Concentration versus time graph for first and second order reactions. State the integral form of rate equation for first and second order reactions and use them to obtain the value of K graphically. And define half-life of a first order reaction. Consider a reaction A gives products. If this is a first-order reaction, what is the rate equation? Click Next for the answer. Click Rate to get the rate expression. The reaction rate is found to be proportional to the concentration of A. To study the concentration as a function of time, click Next. When we increase the concentration of A, the rate increases. Hence, the time taken to form a certain amount of product decreases. What is the effect on the rate of reaction when the concentration of A is doubled? Answer: the rate is doubled when the concentration of A is doubled. What will the rate of reaction be if the concentration of A is increased by 4 times? Click Experiment 3 to find out. Note the variation of concentration of A with time. What happens to the rate of the reaction as time increases? Click Next to see the answer. Answer: the concentration of A decreases with time. Now, note the change in rate with concentration. What is the relationship between rate and concentration? Click Next for the answer. Answer: the rate is found to be directly proportional to the concentration of the reactant. In order to arrive at an integrated expression of a first-order reaction, click Next. The reaction shown is a first-order reaction. Click Rate to get the rate expression for this reaction. Click Next to combine Equation 1 and Equation 2. On combining Equation 1 and Equation 2, we get minus D times concentration of A divided by D times T equals K times concentration of A. Now, click Rearrange. Click Integrate. To substitute ln concentration of A0 for C in the above equation, click C. Thus, the integrated rate expression for a first-order reaction is arrived at. The integrated rate expression is now in the form of y is equal to mx plus c. A plot of ln A versus t is the straight line graph. Click Next to see the graph. The gradient of the graph gives the rate constant K. This is a characteristic of a first-order reaction. What does the point P represent? Click Next for the answer. Answer: the point P represents ln concentration of A0. Another important characteristic is the half-life of the reaction. To understand this, click Next. Observe the decrease in the amount of the reactant with time. What is the time taken for the amount of reactant to decrease from 100% to 50% and from 50% to 25%? Answer: 15 seconds for both. The time required for a reactant to decrease to half of its initial amount is called the half-life. Click the graph button to get the concentration versus time graph. What is the time taken for x mole of the reactant to decrease to 1/4 x mole? Click half x and then 1/4 x. Answer: 30 seconds, which is 2 half-lives. The half-life is defined as the time required for a reactant to decrease to half of its initial amount. This is written as T half. An expression for T half for a first-order reaction can be obtained. Click Rearrange. T half equals 0.693 over K. Thus we see that the half-life of a first-order reaction is independent of the initial concentration of the reactant. Click Next. Some examples of first-order reaction are the decomposition of dinitrogen pentoxide, the decomposition of hydrogen peroxide, and the dissociation of phosphorus pentachloride. In a first-order reaction, the rate doubles if the initial concentration of the reactant is doubled. The rate constant for a first-order reaction is given by K equals 1 over T ln concentration of A0 over concentration of A. K can be obtained from the gradient of the graph of ln A versus time. The half-life is the time required for a reactant to decrease to half of its initial amount. It is independent of the initial concentration of the reactant for a first-order reaction.